In this video, I will trace the Huffman algorithm to illustrate how it works. The problem is that we are given this frequency table of various characters and their corresponding frequencies, and the task at hand is to come up with code words for each of these characters such that if we use such code words, we can compress the text that contains these characters. Now, the Huffman algorithm takes this dictionary C as input, which is basically a dictionary of all of these characters and their corresponding frequencies. The first thing we do is set n equals to the size of the dictionary. Here, this is 6. And then the next thing we do is we build a priority queue out of this dictionary. Now, this is actually a minimum priority queue. So let's just start by doing this. So the priority queue will have items starting from the smallest frequency, smallest values, to the largest value. So we go from F5, E9, C12, B13, D16, and then A45. So this will be F5, E9, C12, B13, D16, and A45. Now we run this loop from I equals 1 to n minus 1, which is up to 5. So at the beginning, I equals 1. Then we start creating this Huffman tree. And the first step is to allocate a new node, G. So we create a new node, G. And then to the left of this node, we set the minimum from the priority queue. So that would be F5. So we set to the left of this node, F5. And then to the right of this node, we again extract from the priority queue and set it. So this would be on the right, E9. And then we set the frequency of this node as the sum of these two frequencies. So 5 plus 9 will be 14, and this will be the frequency of this node. Then we insert this node back to the priority queue. So for convenience, let us say that this node is actually P. So since we already extracted F5 and E9 from the priority queue, so these are gone. And now we add this node P14 back to the priority queue. So once we add P14, P14 will come in right over here into the priority queue. So let's build a new priority queue. This will be C12, B13, P14, and D16 and A45. So this is how our priority queue looks like after this step. Now we go back and change I to 2. So when I equals to 2, once again, we allocate a new node. And then to the left of this node, we set the minimum from the priority queue. So the minimum from this priority queue is C12. So we extract this from the priority queue and we add it to the left of this node. And then we extract again and put the next thing to the right of the priority queue. So this will be B13. And then we set the frequency of this node to the sum of these two frequencies. These will be 25. And let's say for convenience, we name this node as Q. So then we insert this node Q back to the priority queue. So B13 is also gone. And then Q25 would insert right here. So this is how our new priority queue looks like. B14, D16, Q25, and A45. Again, in the next round, I equals 3. So we once again create a new node. And then we set to the left of this node minimum from the priority queue. That would be P14. So this is out of the priority queue. And then we also remove D16 from the priority queue and set it to the left of the right of the tree. And then the frequency of this node is the sum of these two frequencies. This would be 30. For convenience, let's name this node as R. Now R30 will go right into over here into the priority queue. So our new priority queue becomes Q25, R30, and A45. Once again, I is now 4. And then we again create another node. And to the left of this node, we assign Q25. And to the right, we assign R30. And the frequency of this node will be 55. For convenience, let's name this node as S. So when we add this node back to the priority queue, this will go right at the end. So our priority queue now has A45 and S55. Now again, I equals 5. This is the last run of the for loop. Once again, we create another node and extract the minimum A45, put it into the left of the queue, and then S55 and put it into the right of the queue. And the frequency of this new node will be 100. And for convenience, let's name this node as T. So then we put it back into the priority queue. So now the priority queue has T100. So we are done with running the for loop. Now what we have to do is extract min from the priority queue. This is we extract T100. And if we visualize the tree, let's actually unfold the tree to see how it looks like. So this T100 is actually this subtree right here, which is actually 100 followed by on the left, this is A45, and on the right, we have S55. Now S55 is actually this subtree right here. So I can replace S with this subtree, which is actually Q25 and R30. Now this node Q25 is actually this subtree right here. So I'm going to replace this node with the actual subtree. And similarly, R30, this node R is actually this subtree right here. So I'm going to replace this with this new subtree. Now again, this P is actually not a real character. It's one of the subtrees, which is over here. So I'm going to replace this with the subtree that we have. So we have now constructed our Huffman tree, and now the way we can convert this tree or use this tree to come up with codes is to look at this tree and then assign 0 and 1 to each branches. So all the branches that fork towards the left will be assigned a character 0, and all the branches that fork towards the right will be assigned a character 1. So the left child is assigned a character 0, and a right child is assigned a character 1. Same thing again, left child gets a character 0, right child gets a character 1, 0, 1, 0, 1, 0, 1. Now from this binary tree, I can obtain code words for each of my characters by starting from the root node and traversing all the way to the leaf node where my character is. So for character A, my code word will be starting from the root node. There's only one path, so 0 becomes my code word for the character A. Similarly, for the character C, my code word will be 1, 0, 0, 1, 0, 0. And for B, my code word will be 1, 0, 1. Similarly, for F, my code word will be 1, 1, 0, 0. For E, my code word becomes 1, 1, 0, 1. And for D, my code word becomes 1, 1, 1.